So your correlation coefficient goes back to what we're seeing is we had those linear relationships. In the first one we said, like you clearly see it. In the second one wasn't as strong. And then we had that one, it was weak linear. So correlation coefficient is actually going to measure the strength of those linear relationships. So when two variables have a linear relationship, we want to measure how strong that relationship is. A numerical measure of the strength of a linear relationship between two variables is called a correlation coefficient. And I would like to be nitpicky here and say it's going to be actually a linear correlation coefficient. And the reason I say that is because we also have other kinds of situations we look at. We have quadratics. So a correlation coefficient, the one that we're dealing with, only deals with linear looking associations. We're not talking about like quadratic associations or exponential associations. Those exist well. We can make regression lines to them. We can look at strength of them as well, but we're only focusing on the linear ones. So a lot of times this is actually referred to as your linear correlation coefficient or a Pearson's coefficient. So Pearson's coefficient is kind of an older word for it, but you still hear it from time to time. So I'm going to give you this formula here. We're not going to use it that much. So a correlation coefficient. So if you want to know how we do this by hand, it's based on a lot of standard deviations. So remember, we have an ordered pair X and Y. So we have a variable X, and that variable X will have a mean, and it'll have a standard deviation. We have a variable Y, and its data set is going to have its own mean and its own standard deviation. They're both going to, however, have the same sample size. So the correlation coefficient is going to be 1 minus n minus 1. So it's like that adjusting for a sample thing again. And we're going to be, it would be the summation of each x value, or sorry, yeah, it will be the summation of each x value, subtract the mean, divide by the standard deviation for your x's. And then each y minus your mean divided by the standard deviations of the y's. So if we went through this whole calculation, this is what is going to give you your R, or your correlation coefficient. Like I said, just want you kind of understand where this is coming from, but we have our handy dandy TI-84s that'll do this for us, or our fake TI-84. So properties for a correlation coefficient. The correlation coefficient is always going to be between -1 and 1. So it's kind of like your 100%. It's essentially what you're thinking of. It's like one side's 100%, the other side's 100%. If you're at -1 or 1, it is a perfect correlation. The correlation coefficient does not depend on units of the variable. So whatever the units are, not going to have an effect. So if we were talking about, like I said, the sales price of houses, there isn't a unit attached to that correlation coefficient. A -1 isn't -$1. There is no units attached to this. This is just a measure of strength of the variables, or the two variables. It does not matter which variable is X or which is Y. So if we flipped it and we did all the Y's first and all the X's, it's not going to make a difference. We just need to make sure that we can put all the X's together, because we need that mean and standard deviation for X's, and all your Y's together, we need that mean and standard deviation. The correlation coefficient only measures the strength of a linear relationship. It can be misleading when your relationship is nonlinear. So sometimes we'll have things that are exponential linear relationships that look linear. So you might find that when you did a linear correlation coefficient, it's actually very misleading of what the situation truly is. Because sometimes they'll be strong, but it's not a linear relationship. The correlation coefficient is sensitive to outliers and can be misled when outliers are present. So what we mean is, like, most of my data was like this. My correlation coefficient I expect to be really, really strong. Like in this case, maybe like 0.9. It's very, very close to 1. It means it's very strong. And then if I had like a data point suddenly added out here like this, then all of a sudden my data will get pulled towards it. And it's going to pull my correlation coefficient too. So it might all of a sudden drop a bunch because now that data is less related. So it's very sensitive to outliers. And we're going to talk about that too towards the end of this. So we want to use this data here of the square footage and the selling price, and we can want to compute a correlation coefficient. So like I said, kind of briefly explain how this is done if you, for some reason, were inclined to try doing this by hand. These are all my X's. So the mean square footage of these houses, if I looked at all of them and I, add them up, divide by the number of half, that's going to be 2,891.24 square feet. And the standard deviation is 269.5, we'll say that, square feet. Then if we look at selling prices, if I average my selling prices between all those houses, the average price is actually going to be $447,000 with a standard deviation of about almost $30 or $30,000. So we would have to find your mean and standard deviation of all your X's and your mean and standard deviation of all your Y's. Like I said, there may be reasons that you do not want to try to do this by hand. So remember, I need to take each data point, so all my X's, and subtract this mean and divide by the standard deviation. So if I take all my X's, like I said, I'm going to take each one and subtract that mean and divide by the standard deviation. I get all these points. If I took Y and I subtracted each Y from the mean and divided by the standard deviation, I get all this. Then I need to multiply those together. Because what my formula requires to find R is that I need the summation of the multiples of your X minus X bar divided by your standard deviation of X, your Y minus Y bar divided by your standard deviations of Y. So once I do this summation, this data would sum to 6.304143, which we have right here. And then we had 8 data points. So what I divide by is not by 8, but by 8 minus 1, so 7. And this here is my correlation coefficient. So my R is 0.9, say 006. We're going to round it for now. So this is very, very close to 1. So this is going to show that we have a strong positive linear association. So like I said, fortunately, we don't have to do this all by hand over and over again. So we might have to make some changes to your settings on your calculator, which we're going to go through here in a little bit. But if I wanted to take my TI-84 and use it to figure out what this correlation coefficient is, what we need to do is just, once again, we had entered all those sizes and those selling prices. So this is actually Excel, but I would enter this as your L1 and your L2. And what you're going to do is you're going to find calculate when you push on your stats and everything like that. If you move down to calculate, this is actually number 4 in calculate. So like I said, I'm going to show you this because there's actually 2 linear regressions in there, and only one of them will actually give you your R. So this data, we're going to go find that linear correlation coefficient for this data, which we have already entered. So like I said about your settings, so this is my trying to find that linear correlation coefficient. You notice I don't have all my data in here. It's just telling me this A and B, but those R's are not showing up. So if you see that, that means that you're going to have to make a few changes to what's going on here. I'm trying to find the button I need to push here. Just a second. I don't know why I couldn't see it. Mode. So you're just going to hit mode. So one of the first things you want to do is you want to be in classic mode. So you go classic. And you're going to go all the way to the bottom. You're going to turn off your stat wizard and turn on your stats diagnosis. So it should look like this. If you're using the Calculate 84 app, you're gonna have to be really careful because your stats wizard says off then on. So it's gonna it might throw you off a little bit what you're looking for. But once I do that, I go back to stats, go to calculate, and right here, so I see linear regression AX plus B. There's also linear reg A plus BX. We just need 4. This is the one we want. So now you see that I made those fixes. Now that's going to show up. So once again, if you do not see this R in there, you need to go to mode, go to make sure that you, instead of being math print, you're in classic. You want your stats diagnostic on, and you want your stat wizard off. Okay. Like I said, so this data was already entered, and then we go to calculate. Instead of one of our statistics, we do linear regression. So the A and the B, the R squared, we're going to use those later. Oops, let me circle that again. So this right here is my linear regression. Or not my linear regression, I'm sorry, my correlation coefficient. This up here's my linear regression. My correlation coefficient, which is negative 0.874. So we're going to go through and explain a little bit about what these mean for us. Like, what does this mean? So this is kind of telling me a couple things. So when your R is negative, it's telling me that I want to have a negative association. None of that, because it's a linear correlation coefficient, is a negative linear association. So the plus or minus just tells us whether it's positive or negative. And the closer this is to 1 or -1, the stronger the relationship. So you can insist that this is moderate. Moderately, maybe moderately strong. It's not like super strong, but moderately strong relationship. But that's more like what we're going to get into here in a minute. But as you notice here, there is a general trend that we had been seeing in that data that we definitely saw that it looked very close to a straight line. There's a few places where things were odd, like here was a little jump. Here was another place that was a little jump, but it followed this trend where typically when sweets increased, sleep decreases. So this correlation coefficient is just telling us that this is the trend we're seeing. We are seeing a negative association, and we thought it was linear, and it's saying that if it is linear, it's a pretty strong linear relationship. So how do we interpret this correlation coefficient? Well, I just kind of interpreted a little bit for you, but here's some kind of general rules for it. If R is positive, we have a positive linear association, assuming this was a linear relationship to begin with. If your R is negative, like we saw in our last example with the sweets and the sleep, then we have a negative linear association. So this is just telling me the data looks like this. Here it's telling me the data is going to look like this. If R is close to 0, then we have a linear association that is very, very weak. So that was that example where it was like our data points were sort of all over the place like this. So the closer I am to 0, the less of a pattern I'm seeing. The closer R is to 1, the stronger the positive linear association is. So if it's like that, that's a pretty strong close linear association. The closer I am to -1, we're not further away, we're just closer to having a very strong negative linear association. However, this is probably never going to happen, but if it does in the real world, R equals 1, then the points lie exactly on a straight line. Oops. So if R is 1, they're exactly on a straight line. And I'm trying to make this exactly a straight line. And this is going to be a perfect positive linear association. So just sort of hit these big ones here. Then if we have R as -1, then we are going to have a perfect negative linear association. We're going to have dots, our points going straight line, perfectly straight line going down. When two variables are not linear related, the correlation coefficient does not provide a reliable description of the relationship between the variables. So what we mean is, if I see data like this, that's a very, very strong like logarithmic relationship. But let's say I try to draw some sort of line through it. You can see how it almost is very close to being in a straight line. And if I did try to figure out what R is, it might actually come out pretty strong. And it's not because I have a really strong linear relationship. It's because if I look at it as a linear relationship, yeah, it's strong. But that's part where it's a fault of our own. I'm sorry, I'm having a hard time speaking today. A fault of our own for not paying attention to whether this was really a linear association. So this was just to show you once again about what it should look like. So if it's perfectly linear, we get straight line. All points fall on it. If it's like 0.9, it's almost a straight line. 0.5, we can still see a straight line to it. That's a weak positive association, but we can still see where it is. If we have 0, that means there's no linear association. That's when our data is so scattered. There's like no clear-cut line that goes through it. And it's not even clear-cut of it being all going positive or all going negative. It's just a complete mess. -5 or -0.5, it's weak, it's spread out, but we can still see a definite negative trend to it. Strong negative, closer to a straight line, but we're definitely seeing that negative trend. So that's my -0.9 and my -1. That is going to be perfect straight line, but it's definitely a negative association. So this could be a little subjective here, but we want to match the following linear correlation coefficients to the scatter plots on the left. So we'll start with the easy ones. A, we have R is equal to 1. So we know that this should be a straight line and it should be a positive association. So that's going to go here. If I do R is 0.75, we're looking for something that, once again, it's a positive association, not as strong as it is here, but it should still be pretty strong. So we're probably looking at this relationship right here. It's definitely increasing, and it makes a straighter line than, let's say, this one here. This one's a little more spread out. So, or even this one here. That one's definitely pretty spread out. So this one we could probably argue is going to be my 0.75. I've got too close together. We took care of this one. These two, admittedly, are a little hard to tell apart. So it's really either going to be this or probably, no, let me see. Oh, I duplicated a graph, I think. No, I did not. So like I said, we see these two are pretty positive. So let's come back to these two. Maybe I'm not sure about them. So we want to find this 0 here. So this one appears to probably be this relationship. Like I said, we weren't sure about these two. This one's kind of looking positive to me, but these ones are clearly all negative. So it's kind of these two that are ones that are a little hard to decide on. Are they going to be the R equals 1? Oops, there we go. I missed one of these here. I was trying to draw a picture on it. So if I was to make my guess, this one looks like it kind of has a bit of a trend to it. This one does not. I think this one is probably your 0. Like I said, it can be subjective. You could argue with me about that. All right, so now we can go back to some of the ones, like I said, they're a little easier to see. Maybe these two now, because we see we really only have 2 positives left. So it's just the one that looks like it's a little closer to the line. So you might want to sort of like go like that, like which looks like it's a little more clustered. This one does. This is probably the 0.5, and this one would probably be the 0.25. So the more squished it is towards that line, the higher your R should be, or the larger it should be. Unless we're talking about negative numbers, then it's more smaller it should be. Okay, so it took care of all these ones. So this one's easy to find. R equals -1. Then we have the 3 negative relationships left to look at. So this one is clearly a straighter line out of the 3 that are left. So that's probably my R equals -0.75. And then out of these two, once again, which one looks like it's a little more clustered to the line? I'd say this one. This is probably my R equals -0.5. This one looks a little more spread out. This is going to be my R equals -0.25. And this one admittedly was a little bit more suggestive than probably ones you have in your homework. The ones in your homework try to make it a little clearer than this. But like I said, you're trying to look like between these two, which ones look like it's less spread out. This is almost like a big clump or a circle right here. This we can definitely see a trend to it. So this one was why I would assume that the number is going to be larger on it, even if it's more negative. Also to point out, correlation coefficients are not resistant, like we said, to outliers or to extreme values. So a statistic is resistant if its value is not affected much by extreme values. So smaller, large ones, what we call our outliers. The correlation coefficient is not a resistant measure. So if you look at this data, most of it is right here. So this is your area as far as states go, and this is how much farmland that they have. So most states, they have more area, have more farmland, with the exception of Alaska, because Alaska is mostly just wilderness that we don't even try to farm. So because of Alaska, this data is actually getting kind of pulled this way, and you probably get more of a line like this. So the plot shows area of farmland versus total area of a selected state. Alaska is an outlier. Because of the outlier, the correlation coefficient for this plot is going to be -0.119. So they actually think the data is doing this. It's actually seeing a decline because of Alaska way out here. Most of this, we're seeing a positive association, but this point is making it a negative association. So if we keep Alaska, we're going to get this, which is going to tell me that I have a very, very weak, I'm going to say very weak negative linear association. I'm not even sure if you can argue it's linear at that point. However, let's say I just removed Alaska and I just focused on this part here. And this is something we do sometimes. If we have an outlier, it's really throwing off the data, we remove it so we can see what the general trend is. So if we remove Alaska, our correlation coefficient is actually 0.710, as we see right here. This is probably a moderate to strong. There's no like definitive rules about when the border is. So like places like 7 and 5 are kind of like iffy about how strong they are. This is moderate to strong, and this would be a positive now because it's a positive value. Positive linear association. So this is what we mean by that, the linear correlation coefficient not being resistant. Alaska is a very, very extreme outlier. And what we see in this data, which is normally a positive trend, this 1 point throws it into a negative trend. And I've seen this happen. I actually had a data collection for my class once, and it was on how their grade and sleep. And I had one student who insisted they slept 18 hours a day, completely throw off my entire data set. Once I removed them, the data made sense. So sometimes with situations like this, we might actually just remove Alaska from the data because we're looking for a general trend. So we might end up saying, we see a very strong relationship between the area of the state and how much farmland, with the exception of Alaska. You still want to mention that you cut Alaska out, but kind of mention why you do it. Okay, so going back to that data about sweet consumption and what was the other part? Oh, sleep, number of hours of sleep. We see that most of this data, like numbers of sweets they have, are pretty close to each other. Like this is 3 away, 1, 1. This is 2 higher, 3 higher, 2 higher. And then all of a sudden, we get 23. So 23 is my outlier. So we want to know, is it an outlier that's actually influencing anything? So we have outliers, don't always cause changes. We're just seeing this one actually causing a change. So just because you have an outlier does not mean it's having an extreme effect on your data. So if I keep that point of, I think it was 23 and 3 hours of sleep, my correlation coefficient was negative 0.874 approximately. And that is my outlier. If I remove it, we want to see what actually happens to R. Does it really change a whole lot? So we're going to go down. We'll hit delete. And sometimes it won't let you go straight over, but this time it will. Delete. So if you can't like move over to the next place, sometimes you have to go like up and over. Some of your calculators will do that. But I removed it from my data set. So I go back to stats, calculate, go to number 4. Here, my correlation coefficient, when I remove that, changes. So now I get a negative 0.795. So actually removing that point, I caused the association to weaken. But it didn't weaken a whole lot. So that's not a big change. So it kind of has some influence, but not a lot of influence. So what we have here is that sometimes when we have an outlier and we remove it, it makes a big difference to the whole data set. And sometimes I remove it and it doesn't change things very much. So some outliers have influence and some do not. So Alaska is an influential outlier. It influences everything. However, the person who's eating 23 sweets, they're not very influential. They're not changing things much. So I just want to point out that just because a data set has an outlier does not mean it's throwing off your evaluation of the data set. Alaska is really throwing things off. It's giving me data that is completely useless to use when I keep Alaska in there because it's saying that something that we can see is pretty strongly associated is not associated at all. In this case with the sweets, if I remove that outlier, it doesn't change things very much.